CAESES allows you to create flexible CAD models of turbine blades that can be used for fully automatic design studies and shape optimization. Let's assume we have a parametric 2D hub and shroud contour. For the 2D profile design, CAESES gives you the possibility to create your curve parameterization in an interactive way by using the graphical user interface, where you create parameters, points and curves through the menu. However, for more advanced and customized profile designs, you would typically write a so-called feature definition, which gives you more control about all details of your design. You first have to define your parameters as an input for your 2D profile. For instance, things like hub and shroud contour, chord, maximum camber and thickness information, some leading and trailing edge shape parameters, and so on. In the next step, you simply use this parameter input and define how the profile is set up with it. For this task, there are plenty of flexible curve types in CAESES. In addition, you can define helper functions, mathematical expressions, control statements such as loops and if-else branches, import sectional point data, and so on. The flow path can also be analyzed and visualized by using the inscribed circles routine. So, just to make it clear again, CAESES does not contain a set of black box profiles for turbine blades. Instead, you create your own profile parameterizations and incorporate all your ideas as well as your company know-how. The final 2D profile and the 3D section can then be checked and tested in the graphical user interface. In order to create a 3D blade surface, function graphs are needed that describe how the 2D parameters vary in the sweep direction. For axial turbines, the sweep is done into the radial direction. CAESES generates a smooth turbine blade by connecting these function graphs to the 2D profile information. In order to vary the blade, you can now change the function graphs, and the shape modifications are immediately shown in the 3D view. Any kinds of graphs are possible, such as polynomials or splines. Basically, these are only 2D curves where again you can use all the curve types from CAESES. The flow domain for the CFD analysis is also derived from the geometry model and can be exported to your simulation tool of choice. In automated processes, this shape change is not done manually. Instead, an optimization strategy automatically changes the setup of the turbine model. CAESES contains a set of state-of-the-art optimization algorithms which can be used. You can also use your own external optimization tool to change the model. Setting up such an optimization process is super easy with CAESES. Simply create design variables for the things you want to change. As an example, we can vary the y-coordinates of the function graph that controls the chord length in radial direction. Specify the lower and upper bounds of your variable, and this generates a nice slider that still can be changed manually and makes sure we are acting in the correct design space. In addition, you get a convenient overview of your variables with all the bounds. You also have to specify your export data. If you use your own optimization tool, you need to export a new design candidate in a geometry format such as IGES, STEP, Parasolid, Geom Turbo, STL, or even a proprietary format. Just add this export information to the scope that contains the final geometry. That's it. Let's assume you want to use your optimization tool, so your goal is to run CAESES in batch mode. Batch mode means we have no graphical user interface and the geometry generation is done in the background. In the user interface, export the full setup as a so-called FSC script. This script is easy to understand and can be executed by the batch mode version of CAESES. The FSC file contains information about the project, the design variables, as well as the export data. Your external optimization software simply needs to modify these design variable values. For running CAESES in batch mode, use this call. CAESES then loads the project file, sets the design variable values, and through the export call, a model update is triggered. Finally, you find the generated geometry in a subdirectory within the current working directory. With this procedure, you can generate hundreds of design variants and analyze each with your simulation tools on a cluster system. This is how easy you define, generate and automate the geometry generation process for any kinds of products, no matter if you cope with turbines or other engineering components. special geometry modeling approach of CAESES is based on the object dependencies and has been designed exactly for the purpose of automation. As a result, the geometry generation is always repeatable and hence 100% robust. You will find no busted or infeasible designs, which is often the case when using traditional CAD tools. This makes CAESES the leading solution for automated CAD in the engineering sector.